Hi everyone, in this video I'm going to talk about three concepts related to functions and scalability, and then I'll connect this to algorithms and why we care about these estimates when we're writing code. So we're talking about big O, big omega, and big theta estimates, and the first one I'm going to start off with is big O. So this is like an upper bound for a function, and I wrote down the definition here. There's a lot of notation, but we'll do a few examples, and I think you'll find it's actually not too bad. So the idea of big O, so suppose you have a function like g of n, okay? So g of n is your function. You want to know what's an upper bound for the function. How bad could it really be? And so the way you determine that is you say, okay, g of n is less than or equal to k. K is some constant times f of n for all little n greater than or equal to capital N. So let me do an example. I'll come back to the definition. I'll draw some pictures. I know there's a lot of notation in there. So let's look at our first example. So let's say example 1. Show that g of n, which I'll say is n cubed plus 4n squared minus 10. So show that g of n is big O of n cubed. Okay, so what we need to show is that g of n is less than or equal to some constant times n cubed for all little n greater than or equal to some value n. So we actually need to go hunting around and compute the k and compute the capital N. So it's not enough just to write this sentence down. I actually need to do some algebra here. So let's take a look at g of n and show that it's bounded above. I'm really looking for an upper bound. So g of n equals n cubed plus 4n squared minus 10. Okay, so that is less than or equal to n cubed. I haven't done anything tricky there. I just replaced n cubed with n cubed, and I can say that because n cubed is certainly less than or equal to n cubed. Okay, so that's fine. Next, let's look at this 4n squared piece. 4n squared is less than or equal to, I'd like to write it as something times n cubed. Now, I have to think about this a little bit. Is it always true that 4n cubed is less than or equal to 4n cubed? Maybe. You know, it might be just that simple that I could replace 4n squared with 4n cubed. Is that true? Well, let's see. When n is 1, certainly that holds true. And n is 2. Yes, indeed, this will always be true. So I could just replace 4n squared with 4n cubed. And now the 10, the negative 10 there, do I want to write a negative 10n cubed? Definitely not. So I definitely don't want to say, this. This is not true. Sometimes students will try to tell me that's true. They're just replacing n cubed all over the place, and that's not true. For example, when n is, if you tested this out, like when n is 2, you would have negative 10 less than or equal to negative 10 times 2 cubed, which would be 8. And that's definitely not true. So we don't want to say that. But what we can say is we can certainly say that negative 10 is less than or equal to 0. I mean, that's true. That's negative is always less than or equal to 0. So I can put a 0 on the end there. So what I've basically shown here is that g of n is less than or equal to 5n cubed. And there was no restriction on the sort of natural numbers I could pick. So this is true for all n greater than or equal to 1. So here I've solved the problem. I went and I figured out my k value. K is 5. And I figured out my capital N, which is 1. Now, I'd like to hop over to Desmos and show you that I'm not lying to you. I want to show you that this is actually true and show you kind of a visualization of this upper bound aspect. Okay, so I'm over here in Desmos. I'm going to plot my function, which was a g of n. And g of n was n cubed plus 4n squared minus 10. And, you know, we're only looking at natural number values, so I don't care anything about the negative values. So let's just adjust this a little bit. I'm interested in the x-axis going from 0 up to, you know, maybe 1,000. And now my graph fell off the picture, so let's adjust the y-axis here. We'll adjust the y-axis to be, I don't know, negative 20, just so we can see a little bit down there below the axis, and we'll go up to, I don't know, a really big number. Yeah. So I'm just kind of going around there. So you can see that this function g of n, if we put in different data sizes, like if we put in this was an algorithm and we have, you know, computed the number of additions or multiplications that our algorithm does, and we have a data set maybe of 100 people, and we're going through and calculating things, our algorithm isn't too bad. It's pretty quick. But if we all of a sudden have 300 people that we're processing data for, and we're going through an algorithm, and n is 300, we have a 300 size data set, we can see that there's going to be a lot more operations that our algorithm is going to need to do, and that's going to actually slow that piece of code down. And you can see it gets worse. For big data sets, this algorithm is going to be getting slower and slower. So let's take a look at this upper bound aspect. So what I found for the upper bound was, let me just call it y, and that was 5n cubed. So we can see on the graph here that the graph 5n cubed, it's always above my function. It's always an upper bound for my function. So if I know how 5n cubed behaves, it's going to tell me something about how my actual code behaves. So the idea with the upper bound of this big O notation is that we're trying to find just a nice way of characterizing it, like, oh, this function is going to grow like n cubed, or it's going to grow like a logarithm, or it's going to grow like a linear function. And that's how we will characterize the function. I'm going to do one more example. Okay, so now we're going to look at big omega, and big omega is like a lower bound for the function. So now if I'm starting with my function g of n, and I'll use the same g of n as in the last example, we want to show that there is some k times f of n that's less than or equal to g of n for all n greater than or equal to n. So I'm basically looking for a lower bound for my function. So I'm going to write my function over here, g of n. And what I want to say is I want to say that g of n is greater than or equal to something. I'm looking for k times n cubed. That's what I want to show, or that's what I need to show. All right. So my g of n, we know, is n cubed plus 4n squared minus 10. That's what g of n is. And I want to show that it's greater than or equal to some constant times n cubed. So let's replace each term. Now the first one, n cubed, is greater than or equal to n cubed. So I can just replace that. So that's because n cubed is less than or equal to n cubed. I did nothing tricky there. What's challenging to me is that it's hard to argue that n squared is greater than an n cubed, and certainly negative 10 isn't going to be greater than positive valued terms. So for that reason, I want to look at both of these together and say these are greater than or equal to 0 for all n greater than or equal to some number. Now, when n equals 1, certainly we're going to have 4 minus 10 is negative 6. So I can't put n greater than or equal to 1. If I want to look at n equals 2, now we've got 4 times 4, which is 16, minus 10, that's a positive 6. And now we're getting positive values here, which are indeed greater than or equal to 0. So I'm going to put n greater than or equal to 2. So here we have it. We have n cubed is less than or equal to g of n, or n cubed plus 4n squared minus 10, and that's true for all n greater than or equal to 2. So I accomplished my task. I found my k value, which in this case is k equals 1, and this capital N over here was my bound for the n's. That was 2. Let's go over to Desmos. So there's y equals n cubed in Desmos, and so it looks almost like the green line is overlaying the red line. So let's zoom in a little bit to show that it is actually a lower bound. So I'm going to zoom in a little bit on my curve. And if we zoom in enough, you will see that indeed the green line, this n cubed piece, is definitely a lower bound for my function.